So welcome everyone. This is the fifth week, or rather, this is the sixth week of the Quant University Fall School. And the theme of this school has been machine learning in production. And we have looked at various facets of machine learning, and we have run 3 courses trying to kind of bring people up to speed on the various innovations which are happening out there. But the key area still is that when you think about machine learning in production, there's so many open problems for research. And when we think about how do you make sure that you deploy these large machine learning models into production, you have to start factoring in all the key areas which you have to think about in terms of whether these are usable, whether these are interpretable. We really make sure that the actual outputs are usable in a production setting. So today, we are fortunate to have Dr. Augusto Giento, who is leading all these efforts at Wells Fargo. Now, the domain at which, the scale and the domain at which Wells Fargo operates, they have to make sure that all these models are thoroughly tested, thoroughly vetted out before they can deploy in production. And when you think about adopting these kinds of models into production, you have to start not only looking at the workflows, but you have to do intense research on making sure that you understand what these models are actually doing. And Dr. Augusto has been in the forefront of innovation in model risk and making sure that these models, which are currently being designed and deployed, are actually usable and interpretable. And in the last 6 months, we have exchanged multiple notes, and we had Dr. Augusto present in our summer school. That lecture was very well received. So we invited Dr. Augusto to come back and talk about his latest research and the beautiful package Augusto and his team have developed called Aletheia. And I would love to kind of see how we can bring that onto the sandbox and start playing with that. So welcome, Augusto.
Thank you, Sri. Thank you for the kind introduction, and hello, everybody. I browsed through the attendee list, a lot of very familiar names from the very, very old days, back to my old days at Ford Motor Company too. So thank you for attending, and we're going to have hopefully something that's fun and very useful. We're going to talk about something very, very practical. Sri talk about research, but what we do is really something that we can deploy and benefit right away. This is what we really keen about. Our research is very, very different from academic research. Our research is really more how they're talking about the practical aspect for real world. So this is what I'm going to share today. So I'm going to let me do share screen. Sri, can you enable me to share my screen?
Yeah, give me 1 second, Douglas. I thought I had done that already. Give me 1 second again. Okay, so you should try it again, guys. Yeah.
Yeah, I can do it now. I'm sharing my screen. So let me do this one. I hope everybody can see it.
Yes, we can.
Yeah. So my topic today, talking about self-explanatory model. And in particular, we're going to talk about deep ReLU networks. So how to make deep ReLU networks interpretable. This is very, very important. Now I'm going to talk a little bit why is that, and we're going to talk about the interpretability. We're going to talk about how to diagnose the diagnostics, as well as the how to simplify it. Simplification is very, very important when we're dealing with neural networks, because with machine learning in general, with neural network in particular, because you want to control the model failure. You want to make sure that you deliver, you have safety in the model. So controlling model failure in real world, in particular in high-stake environment, is very, very critical. The We have a paper that we put out there, and I have the link here in archive paper that you can read at your leisure. I'm going to go through the topic that I covered today. Majority of them, not all of them, majority of them are covered in the paper, but I'm going to present it in a way that is very, very understandable. So we're going to skip the math and try to understand what this thing is. Sri also mentioned the Python package that we make it available. So you can download and you can run it in Google Colab. You can try Google Colab if you want to, or you can do it in your machine as long as Unix machine. The package is named as Alesia, after the goddess Greek of truth, because that's the intent here, revealing the truth, what is in a deep learning, particularly ReLU deep learning. Okay, I want to give a shout to some of my collaborators, a few of them. In particular, the first name is William North. He was a summer intern, so you can look at his paper as well in my LinkedIn link. His paper on related subject to this, how to do what we call it as a flattening the network from deep network into a single layer wide network, the equivalent, or to do simplification. So feel free to look into that as well. I think Wilnot is looking for summer intern. I want to bring him back to Wells Fargo, but because he's so smart, I want him to experience other areas. So if you guys, any of you, looking for really, really sharp guy, that right there. Okay, so let me start with this. Let me start with the explainable machine learning, because people talk about explainable AI, explainable machine learning, and all those things. I want to keep I want to put my perspective. You feel free to disagree with my perspective, but this is my perspective. One is a lot of things tool that out there is all about post hoc interpretability. Lime, SHAP, PDP, QII, and ALE, and all of those tools are post hoc interpretability. You have a black box model, and then you apply this post hoc interpretability tool to explain what the model does. I have reservation for all of this tool, even though I myself did research in this subject as well, but I have a heavy reservation to all of this tool, because first of all, if you have to explain the explainer, any of those tools are explainer. If you have to explain any of the explainer, you have started not in a good spot, because the explainer is not easy, it's complex, and worse yet, they are not exact. So they can be wrong, and many of them are wrong in many situations. So just be very, very careful when you use a post hoc interpretability. Take it with grain of salt, apply multiple of them, and sometimes the outcome is contradictory to each other. That's the nature of the tool. So I am not a fan of post hoc interpretability, as I said. Second approach is model distillation. From complicated model, then you distill it into something simple. For example, complex model, then you explain it with tree, or model-based tree. It's basically tree where the nodes is linear regression, to be able to explain that. We have a paper as well in archive that feel free to read. But what I want to talk about today is really something that I feel like it's something that we ought to do, which is employing self-explanatory model, employing a model that's really, really interpretable from the ground up, instead of using post hoc interpretability or model distillation and so on and so forth. Just apply model that's interpretable or self-explanatory model. And to do that, you don't have to sacrifice with the performance. You don't have to sacrifice the big trade-off between performance and interpretability. That's what we're going to talk about today on ReLU DNN. So there are a few streams that people can do. But one of them is like really constraining the architecture of the network. That's what explainable neural network or XNN or the adaptive explainable neural network is really constraining the architecture. So you can do that way. Or today's discussion is we not going to do a constrained architecture. We're going to do a full ReLU network. So that's my view. Yeah. So if you have a choice, especially in high critical environment, don't use explainability tool. Build model that's from the ground up really interpretable. So that's the theme that we're going to talk about today, the methodology, the techniques that we're going to talk about today. Okay. So I'm going to talk about 1 minute of neural networks here, so that just to ground everybody up. Yeah. In statistics, we have linear model, very simple linear model, and then when we're dealing with nonlinearity, we use spline. Okay, so basically we apply basis function for each variable. Then you have nonlinearity. The simplest thing is piecewise linear. So like I show in the picture on the top left picture is piecewise linear. This is exactly what ReLU basis function is, or rectifier linear unit. Basically, you have a cut for the linear function. If the value is bigger than 0, it will be linear. If the value less than 0, it will be negative, or 0, it will be 0. Okay, so it's on and off. If you think of it, the local linear model will be on or off. If you want to do that and implement it in a neural network, yes, you can. So basically, you implement it as ReLU basis function on the right-hand side. So you use ReLU activation function. So you have the ReLU activation with the not location that not known as we call it not location in spline. We call it as bias weight in the ReLU network. So that's a univariate model. Is very simple. In multivariate, statistician to project it first. So from multivariate variable, you project it, you apply projection matrix V, so becoming a univariate, and then you apply the ReLU basis function. That's called single index model. And single hidden layer network is basically a generalization of that. So instead of a single index projection, you do for each projection you have multiple projection. For each basis function, you have different projection. That single hidden layer network, in a way, you can look at it almost like a multi-index model in statistics. So that's the way we look at neural networks, right? So now, how about if we're talking about the deep ReLU? So I'm going to give a very, very simple example. Deep ReLU is basically just you put multiple layers. So instead of just a single layer, you put multiple layers. So very simple. The output of the previous layer become input to the next layer. So it's very very simple here. And let's see what this thing get a little bit more insight. So don't worry about the weight matrix, or the bias. That's the what written and below. So I just created a stylistic example using choosing this matrix for the weight to illustrate what the multiple layer do, right? So the first layer, we only have 2 nodes. So if you have 2 nodes, node 1, you have data. The data subjected, you enter the data. Node 1 is on. It can be node 1 is on, or node 2 is on, or both nodes are on, meaning that if nodes 1 on, you have that linear equation from node 1. If the node 2 is on, you have linear equation from node 2. If both on, then you have a weighted average of between the 2 linear equation to get a new linear equation, right? So what the network does is basically the picture that I show here on the left is doing data partitioning. So 0, 0 is when no node is on. So basically the value is less than 0. Output of the neuron is less than 0. So the ReLU clip it into 0, right? So 0, 0 is no node is on. 0, 1 mean that node 1 is off, node 2 is on, 1 0 node 1 is on, node 2 is off, 1 1 is both nodes are on. So any data that coming in, it will be mapped into this for region, right? So the first layer of the deep network is basically, in this example, simple example, partition the data into for region. So any data will go into this for region, and then from that, the output of that will go to the second layer. So the second layer in the previous example, I showed I have 4 nodes. So with that, similar things with that, yeah. So the data is get partitioned further. So you can see it there, an example of the partition. So with that, what the deep learning does is basically do data partitioning. So if you think of it, it's almost like tree. Tree is doing partitioning, but tree doing partitioning based on one variable at a time. To partition, so based on the equation, right? Based on the linear equation, you partition it. So it's more flexible than tree. So that's one thing. The structure is more flexible than tree because it's not one variable at a time, but based on the combination of variable. Those some people call it oblique partitioning. The second thing that's different from tree, in tree, the partition is only going forward. So you partition one according to one variable, you freeze that partition, you partition next, and so on and so forth. During the training in deep learning is to back propagation. So the partition from the first layer, the shape can change because of that, right? So adaptively do that. So the partition from neural network, of course, is more powerful than partition of the tree. First is because of the shape, more flexible, and tree shape is a special case. So that's the first. The second things is the back propagation, partitioning it iteratively layer to layer instead of just going forward only. Of course, you can train network layer per layer, which some people do that too. If you do train network layer per layer, then becoming more like tree. Okay. The key concept here is what we call it as activation pattern. Okay. The activation pattern is basically which node are on for each layer. Which nodes are on each layer that define partitioning and define the data partitioning and define linear equation. Because once you fall into a certain region, it become linear. If you think about the first layer only, right? Node 1 on, node 2 on, or whatever is a linear equation. And then in the second layer, combination of linear equation, it will be still linear. So for each data, it will be mapped into partition corresponding to the linear equation or local linear equation according to the activation pattern. I'm going to skip the math, but this is discussed in the paper. But basically, what we can do is we can extract the activation pattern by running data point per data point. We can get the activation pattern, which nodes are on or off for each data. And with that, you can extract the W, the weight, that's from many layers into simple weight and into the bias as well. Those you have local linear model. So for each sample corresponding to a region, corresponding to local linear model. Now, you can have many of them because of that. The expressivity or the capacity of network defined by the number of nodes and the number of layer that define how many local linear equation. That's a very, very large linear equation that you can get, that neural network can capture. Let me give a simple example, to what I'm talking about to make it less abstract, because this is a key concept to for the discussion, the rest of the discussion. I have an example here, very simple network, 3 nodes on the first layer, 2 nodes on the second layer. I have data input, x1 equal to 2, x2 equal to 1, so you can trace it. Going to the first node output is 10, so the node is on. Going to the second one, the output of the node is 0. As you multiply it with the weight, it's off. So and so on, you get 1 is on, right? And then from that, you get propagated. So linear model with output of 10, linear model with output of 1, you get combined, will become another linear model with output of 13. Okay, so that's the final equation for this data to this network is x1 plus 4x2 plus 2. So you can get, you just run it data per data, you can get this. The unwrapper package that is in Alasia do all of that for you. Yeah, the Alasia package that is in GitHub do all of those, so you don't have to do it manually. Do all of those. When you got that, when you run it, you got all the activation pattern, you got all the regions, so that's the output on the right hand side. Yeah, you got the region 0, region 1, those are the partition for done by the network. And each of this partition, how many data points, that's the percentage of data, whether they are, how many is in belong to class 1, how many belong to class 0, what is the accuracy, training accuracy, what is testing accuracy, and some of the statistics that you can get from Alasia. Okay, in this example, we've the network done 18 from 0 to 17, 18 linear equation. So and you can plot each of the linear equation, what are the coefficients. So that's what I did here in an example on the bottom left, plotting variable and the coefficient of each linear equation. So you can see I just do simple parallel coordinate plot to see what are the coefficient of all those linear equations, how different or how similar they are. So very, very similar to do parallel coordinate plot. Alasia package gave you all of those. Okay, so that's just a quick things that what it does at the end of the day. Deep learning, ReLU deep learning is I don't want to disappoint you, is basically a segmented regression. Yeah. So deep learning, deep ReLU, whatever deep, however wide, when you train it, what they do is basically segmented regression. Of course, it's segmented regression in steroids because the segmentation is data-driven. Remember all the partitioning that we talked about, the network partitioning in a way that local linear model work best. So one is data-driven. The second thing is it can be so many of them, a lot of linear models. So it's not like 1, 2, 3, or 4 segmentation, but it can be 1,000 or 1,000,000 of them when we're going to revisit that a little bit later. Okay, this is what happened. So when we extract all those local linear model, the network construction, the network that you have very, we call it p-expressivity. You can have, it can contain a lot of, for example, if I just do a single layer and I have 3 nodes, so I can have 2 to the power of 3 minus 1. So you can have a 7 equation with 3 nodes, you can get 7 equation. So in a single layer, if you have D node, you have 2 to the D minus 1 linear equation. That's a lot, let alone if you have now deep network. So you have a big universe. When you run your data, with training data, not all of them are exposed to. Not all of them get data. So this is something that we need to be very, very mindful because people are not thinking about this. Not all the linear equation in the network exposed to the data. So if that's the problem, it's we have problem with the reliability, how trustworthy the network is, particularly in the region when we don't have enough sample, when the sample is small or never get exposed. So when you run your test data, when you run your testing, some of them are overlap. The region that has training data exposed to training data, region also exposed to testing data, or region that's never get exposed to training data. So that's something that we need to diagnose. We're going to talk about diagnosing. So it turned out that if you use neural network, only a small portion of network, small number, a portion of local linear are really used by the network. Small number of activation pattern. Number of LLM, local linear model, is much, much smaller than the expressivity of the network. That's in real world, in most of application. Unless you have humongously big data and a small network, that different story. Here is the thing as well. Many local linear models only have single sample or single class in classification problem. So if you have linear equation, this is from your regression class, from basic statistics. If I have P variable, I need at least P plus 1 observation to get a good regression equation. So in network, it's not like that. You know, many locations only have single sample, those less reliable. So this, I give an example here, table on the right side. You can see the how many region, a lot of region in this case, 155 regions. And how many sample in each region. When you run Alicia, you'll get that and get summary. And you can see here a lot of region have one observation. The response mean in this is like for classification problem, you can see is it a single class or two class. And then you can get the local MSE in this regression problem in this example, local MSE and global MSE. Local MSE is what is the mean square error for that region, only the data in that region. Global is when I run all the data into that region, how good is that local linear model? We're going to use it for model simplification and diagnostic later. Okay, so now if we have the LLM, if we have local linear model, we have local exact interpretability because we have the linear equation. Unlike Lime or Sharp, okay? Lime and Sharp is not exact. So they are it's through perturbation or through sample. Yeah. Here we got exact local interpretability. We can do box plot, so you can see the equation how the different local linear model have different coefficient. You can box plot it. You can parallel coordinate it to see how different they are or how similar they are. Right. We can look at the importance calculation, local linear importance, and we can look at the interaction and look at the main effect as well in a very exact way, and we can apply statistical inference locally as well if you want to. Okay, so let me give you an example here in terms of, because a lot of people, and Sharp is very popular, Lime is very popular, so I picked 3 examples in one region. So that's the label. You see Deep Sharp 3 or Deep Sharp 2 or Deep Sharp 1. Those are different sample. So Alicia is the exact, because that's the local interpretability, the exact equation. Yeah. And then when we apply Lime or kernel Sharp or Deep Sharp, you see how different they are. Yeah. And some of them can be very wrong. You can look at the variable that's important or not important. It can be very wrong. So look at the inconsistency across the board when you compare Lime, kernel Sharp, Deep Sharp to Alicia. Alicia is the truth. It's a local linear model, the local linear model that we extract from the network. So when you use all those explainability tools, be very careful. This is why I'm not a fan of explainer. I'm not a fan of explainable machine learning. If I can do interpretable machine learning, like what we're going to talk about here in a deep ReLU, which is basically is very interpretable, I pick interpretable model anytime. Okay, feature importance. So we can calculate, given you can look at the math in the paper, but you can see how important one variable. We can look at the effect plot, just like in statistics, but now the effect plot has to be local, right? Because we have so many of them. So locally, pick a region that's big enough. You can plot what is the effect of each variable, and you can look at the distribution as well. We can look at the nonlinearity. So this is I'm just simply plotting the coefficient of the regression to variable, and in this example is Boston housing data set, a very well-known data set that is in scikit-learn. So for this, you can see what is the weight, what is the coefficient, and I'm only plotting the centroid of each region so that it won't be too crowded. So I'm plotting the centroid of each region, and the weight. So the diagonal is basically give you main effect. The diagonal give you main effect, and then the off diagonal, after you remove the main effect, you plot the same thing, you can get the interaction effect. Okay, how one variable in this example, how the crime rate interact with the lower status of the population for house price, right? So you can get this as well. This is very, very important in the diagnostic. We remember in the previous example, in the let me go back to the table a little bit. Alicia table, when you run it, you get the table, calculate local performance locally for that region. What is the performance? And then we compare with global. If we run all the data into that local linear model, how good or how bad that one is. So that's what is plotted here. Yeah, two examples that I use. The top one is about Boston housing. So it's regression problem. So we plot mean square error. The bottom one is classification problem. This is FICO HELOC data, the data that was used for competition a while back. FICO HELOC data, the data that used by Cynthia Rudin in her paper. So you can see this one here. You run the network, you can see the locally it's very, very good. The mean square error is good. So when you run all the data to that local region as expected, it's not that good. Okay, so that means the model really you need a lot of interaction. You need really a lot of segmentation. And this is the opposite here in the FICO HELOC data. Locally, globally, regardless, they are performing reasonably well. Yeah, all the local linear model, different local linear model that the network found, when you apply all the data, they are reasonably almost the same performance. When you have something like this, it tells you that basically you have redundant, unnecessary local linear model. A single linear model will do a good job, which actually that's what it turned out. When you run FICO model, you run through Alicia, you can get this thing, an indication, I don't need complicated model. Heck, I only need one model. So when you run logistic regression, voila, you get a very, very good result. But from this diagnostic, you can simplify your deep learning into a more simplified model. We're going to talk about that in a little bit more detail. Okay, so I'm going to give an example. This is the danger of deep learning. This is why it's very, very important to extract all those local linear models. So Sarus and my team created very, very simple example using simulated data. So this is the top equation, the data generator. Very, very simple linear model. You generate data, and then from those data, we fit 3 hidden layer neural network, each with a neuron. And that's, even though the model looks small, but it's not really small. Remember, even it's a single layer with 10 neuron, you have 2 to the 10 minus 1 equation, right? So a 3 layer, you have so many of them. So you do this one, you run it, you train it, and then you test it, you split the data, you train, you run through this, you get the AUC on the validation data set, on the testing data set. It's very, very close to the how good the model can be, you know. So we created a data that as best as you can get is 0.835, right? And this model, it looks very, very damn good. Looks very good, very close. The AUC is very high. So it's I'm happy. Is it? Should we? Okay. So that when you extract the local linear model with the methodology that we just talked before, it turned out with this data set, with this network and this data set, we have more than 3,400 local linear model, more than 3,400 regression model. That's what you get. Okay, more than 3,400 regression model. It turned out that more than 2,100 only have one observation. 63% of the local linear model, 2,100 of them only have one observation. So, and then let me plot it now. So I'm plotting on the x6, yeah, on the x6 at the top equation. The coefficient should be minus 0.8. So that's, and I plot it. So the horizontal plot, the horizontal is the coefficient, and the vertical is count how many sample in each region. Yeah. So every circle here is a local linear model, and I'm only plotting the x6. So it should be around green because that is minus 0.8. So the region, the one that remember 2159 is single observation only. That's the one at the bottom. That's the coefficient of the regression. All over the place. Yeah. In fact, some of them are positive. Okay. Some of them are positive. So as you go up to the scale, the sample size becoming larger and larger, the coefficient is more correct, closer to minus 0.8. Yeah, the region with large sample, they are more correct. Very logical, just like in statistics. You know, large sample, your larger sample, your regression estimate is more reliable. Less sample, your regression estimate less reliable. So it's direct, just like in traditional statistics. So here's what I'm talking about when we talk about model safety. Think of it, this is the deep learning doing self-driving car, the deep learning driving Uber car a while back, right? It should be turning left, the value is negative. It's turning right, the value is positive, because for that specific instant, it's using the wrong local linear equation. So we're talking about model safety here now, okay? Literal model safety, depending on the use case that you have, right? For that data, it went to a region with local linear model that the coefficient is wrong. That's what we're talking about in the DNN problem here. And this is very, very typical problem in deep neural network. So let's bring to the next point. Can we simplify it? Because simplification, can we take advantage of that? Simplification, can we merge? Can we reduce the number of local linear equations? So we have created a very simple toy problem, classification problem. Data is in a circle. Class 1 is red. Class 0 is blue. So we run deep learning. You get all the green color there, all the local linear equation from deep learning. Many of them, right? So all those local linear equations. When we merge it, we simplify it, we can end up with 8 linear equations that probably as good as. So on the right-hand side, it shows you how the simplification that you can reduce into 8 equations only instead of thousands of equations. When you have 8 equations, you know all the equation is, you know all the equation are, you know how the model will be working or will not be working, right? So it's very important to ensure. One is what we call it as conceptual soundness. If the effect is positive, if the effect of unemployment to default is positive, it needs to be positive everywhere. It helps us to, so we can now evaluate conceptual soundness, not only testing model output based on AUC, MSE, or anything, but we can also evaluate the conceptual soundness of the model, looking at the coefficient, whether it makes sense or doesn't make sense, the direction. So that's the very, very important things. Improving interpretability, lesser model, you can understand it more. 1,000 model or 100,000 model, you have to understand 100,000 model. You have to investigate all those 100,000 model in terms of the equation. Very quick things that we can do before we're using a box plot. Before we're using box plot, if it's need to be monotonic, all the coefficient need to be all positive or negative. It cannot be both sides because that will be non-monotonics. So a quick check that you can do, by using box plot in terms of conceptual soundness of all the linear equation extracted by the deep learning. Okay, so that's controlling model failure. I talk about controlling model failure because we know a lot of LLM, a lot of local linear model are wrong. So we need to be able to control it by having less local linear model. You control models failure, you ensure model safety. So you have a choice coming up with big data using a large amount of data to train. So make sure every LLM get exposed to enough data, or you simplify. So when it's simplified, and you can see here in the example of simplification, the original deep learning partitioned the data in very complex way. That's the chart at the bottom left, right? And when you merge it, it merged into 8 regions only. So that's the merging algorithms. When you read the paper, it has the merging algorithm. It merged it, a neighboring wide, and merge it to simplify the model. And that's become only, in this example, is only a much smaller number of models. We still use the original network to do data partitioning, then do a lookup table. If you belong to region 100, you use equation number 2. You region 102, you use equation number 3. So you can employ a lookup table when you use it for prediction. So that's the merging case. Then we can also do what we call as flattening. From deep network, I can simplify it into a single layer network. If I end up with 8 LLM, I can collapse that into 8 nodes. That's more than enough. 8 nodes, single layer network. That's what we call it as flattening. Some of you that work on edge computing may want to do that because computationally will less resource. So now you can deploy much smaller model in that edge computing environment. So that's if you want to do flattening. That's this very simple step that you can do. I want to put a simple example here in the real data home lending. So we took home lending data that's originated from 2004, 2014 home loan. We took sample and we ran it. So you get and I plot the coefficient of the local linear model. The bottom there, you show the variable, what variable there, and you plot the local linear model coming out from original DNN. We run the merging algorithm to simplify it. You got simplified model. It turned out in this situation, we only need 3 models. Okay, we only need 3 models instead of thousands and thousands of models from original DNN. So as a result, simpler model, more interpretable. And by the way, when we look at the performance, the training AUC, ReLU DNN, the original network, the second table, and the merged one, that's from the merging, and then from the flattening. You see, the flattening, the merging is not any worse than the original ReLU DNN, and the flattened network actually better, right? Simpler model, you don't need the complicated original model. You have less number and more, and you can interpret it as well. If you boil it down into 3 equations through 3 local linear model, you can see clearly the segmentation that the deep learning does. Basically is segmented into 3 regions. One region is that is on the right hand side. You can have region that is really you can look at the high FICO or low FICO, high LTV or low LTV. The green color is really the green color. If you see here on the bottom right corner, the green color is really low credit quality, low FICO, high LTV, and also the delinquency status from early delinquency to late delinquency. So you can see what the network partitioning. I have another example on the how we do convolutional neural network, CNN, text classification model. The paper is published in arXiv as well. The paper is using SHAP, not using this. It was just to demo, because the purpose was demonstration of how to come up with a interpretable model. In text classification, the problem is mainly, I'm going to talk about this in a little bit, not much because we run out of time. It's really when we do word embedding. We do word embedding, now become the data become mushed together. It's not very interpretable. So you can use CNN to make it interpretable by to create the features that corresponding to n-grams basically, and then you can deploy it and you can look at it. In this example, I'm just do a quick things. In this example, actually the local linear model, once we look at it, it's in this example it has 663 local linear region. 401 of them has sample less than 5. Okay, and 190 region have only 1 sample. It's the typical problem with deep learning. So you can see the coefficient, they're almost the same. When the coefficient almost the same like this, I plot the coefficient with parallel coordinate plot. Then you say you don't really need deep network. Simplified model. Your convolutional layer did such a good job. It created features that a simple linear model will work. So the magic is when you train it, the convolutional layer, in this case using 150 filters, created features that linearly separable. Because linearly separable, you can remove your DNN, your feed-forward, your fully connected feed-forward side, post-convolutional network, replace it with logistic regression. But the magic when you train it here, the convolutional layer learn to extract n-grams, 150 with the 150 filter, so that the problem becoming linearly separable. So I want to give enough time for question and answer. We have 12 minutes here. So Sri, I wanna do it for Q&A here. Sri, seems like a lot of questions. So would you help me to read the questions, Sri?
Absolutely. So I think, so Pierre, thanks for all the questions. I think Pierre has been, if he was in my class, he would get an A because he has put in like 5 or 6 different questions. So the first question is it possible to analyze with the region where there is no observation? For areas where there are no observation, is it possible to analyze?
Of course, because you can see the local linear equation, right? The coefficient compared to the rest. The one you can extract things that not being used, because that is a very good point. Because that is, let me go back, because that's where the dangers are often,
Mm-hmm.
Hang on, let me go to my Venn diagram. Okay, that's the Venn diagram, right? A lot of region not exposed to any training or testing data. So this one here, your testing data that doesn't intercept with your training data, that's local region that's not exposed by training data. You can check how good they are, how trustworthy they are. So for me, when something like that, I will remove it. I'm going to control it as I reduce it to much smaller number of much smaller number of equations, so that if I fail, I know how this thing going to fail. Because right now, I don't know how this is going to fail. Right. So what the deep learning people do? Well, they invented all kind of techniques to do that. Counterfactual testing, right? Counterfactual testing is trying to do that. Let me test randomly or whatever, find using counterfactual if this model will work. Because we don't know what you don't know in your network. That's the problem. So I chose, instead of doing that, that's not robust, because that's how good with your counterfactual test. How good is your robustness test? I would rather extract the equation that I know is trustworthy, so I know how the model will fail. So I'm going to use this example, okay? Because that's question related to my last slide that I want to use. Oh, I don't have it, but robustness tests. I spoke about this in my past talk, but you can do robustness tests, because in each region, you can look at sample, how close the closest sample, you can perturb it, it will flip to get to the other. So if you know all the equation, you control it, you know the limit. The problem is you deploy This deep learning is very powerful techniques, but it's a beast.
Right.
If you don't control it, it's a beast. You have to tame the beast. This is what Alicia is trying to do. Try to tame the beast. Understand what the model does, really understand it. And by the way, it's a good thing. For example, ReLU DNN. I would argue ReLU DNN way more interpretable than GBM base 3, okay? 3 boosted 3. Because boosted 3 is not interpretable. Those you use explainer and all of those things, right? I would worry honestly, use a tool like that. This one here is interpretable, but it's a beast. So you have to control, you have to tame the beast. If you don't, you're going to have all those kind of problem, region that don't get exposed to data. Yes, you can.
Absolutely. So actually, I had a question. I didn't type it. So have you looked at other activation functions other than ReLU?
Yeah, it's a good question. It's more complicated. You know, we do ReLU because it's on and off as linear. You can do it. Yeah. So my point is this. I like ReLU because it's very clear, very interpretable. Some people want to use sigmoid, tangent hyperbolics. Well, if you can solve it with ReLU, why bother to use other things that less more difficult to be interpretable? Okay, so we're not able to come up with a theory that as clear as ReLU. That's the thing. So and then you're dealing with a piece of the beast there.
Right, absolutely. And Amir has a question. To get the coefficients using conventional DNNs, can we just take the weights above threshold to get the activation pattern instead of a ReLU network? Kind of doing thresholding instead of ReLU?
Yeah, just do the you just look at whether on and off. Basically, what it is you can do it manually if you want to. Which one run it, which one is on, which one is off. The one that's on, those are your activation pattern, right? So basically, what network has, if you remember the lottery hypothesis paper from MIT, right? It's only small network, a sub network are really being used. You have to find that winning lottery, right? So that's this is exactly the same thing, just show it, get the winning lottery, right? And so get all the sub network. So each LLM is a sub network.
I guess, I'm wondering, I have to look at the architecture of Alicia. Is that something we could extend the unwrapper to kind of do something like that?
Yeah. The unwrapper gave you that. Basically, what's on and off. You can extract. You can get the output from Alicia. What node is on and off for each data. Yeah, you have it. You get that in Alicia. You get exactly all those. What are all the configuration? What are all the sub networks that's really used?
Absolutely. So I think Pierre has a couple of other questions, and I don't know how much we can take, but I'll try to summarize some of them. Questions surrounding sparsity of observations and expressivity of neural networks. Are there any measures which we could potentially use in order to kind of look at the sparsity, and you've kind of given like specific regions, very sparse regions, no data, and then having very few samples. How do we express those in terms of specific measures?
Yeah. We don't have a specific measure right now, but what we have is, if you look at the output, we just give you a very simple, how many sample in each region. Yeah. So we gave you raw data. If you want to come up with a measure, I'll be delighted if you can come up with a measure and learn if that's very useful, hopefully useful. Right now we just give you raw data. Okay. The Alicia give you how many sample in each region.
I'm thinking in the context of maybe tying that to uncertainty quantification in some ways, where there are very sparse data sets.
Yeah, I would be as simple as draw a histogram, right? Draw a histogram of number of sample for the region. Then you can see. I would do that. Just I'm histogramming the count.
Absolutely.
Yeah. So that's actually something that what we did like this. So we just histogram it. We look at it. Okay. So you can see. Yeah.
Absolutely. And then the other question is, oh God, we have 18 questions. We'll probably be here for the next hour or so.
Well, I have to jump off to another meeting, unfortunately.
Okay, so I will collect the notes, and maybe we can discuss offline to see how we can maybe get some of the summary and post it on our Q Academy page. That way people can access the answers.
We can do that.
And I'll also share it with the people who are on. So let's take a couple more questions.
I know this is really rushing. You know, we do a 1 hour. I think Sri, you need to do something that likes more like workshop, so people can try the tool and have a lot more discussion, trying different data. I think that's what we do. I hope that I just initiate an appetite here. You know, that we can make deep ReLU into a very, very interpretable model, self-explanatory model that we don't have to use. This is what I say all the time. When it's explainer to me, explainer to machine learning is like MSG in your food. It make it taste good, but I don't know what that MSG do for you. Okay,
right.
So I like model that has no MSG, pure self-explanatory. So that, and then the second thing is deep ReLU is very powerful, but it's a beast. You have to control it to get to the model safety.
Absolutely, and just to add to that, you know, as we have discussed, so it's coming in Q1 when we do the winter school. We will have an explainability and interpretability workshop. Kind of, you know, doing the big picture, like what's out there, and some of the practical techniques. And I think we'll share more details with the audience later about that. The question on pruning, you know, can we use this methodology for pruning neural networks? And I mean, like you kind of brought it down to a single layer kind of thing. And is there like additional, you know, can you like dictate how much pruning you could potentially do?
Yeah. Actually, there's two things that can be done. Okay, the paper that by Will North. Okay, Will North. The paper, if you study what Will North did, so he did that deep network, extract all the LLM, 1,000 of them. You flatten it, so each LLM is a node in a single layer network. Then and you fix it, and then you become regression problem, right? Then you can apply regression regularization L1 or L2 to prune it, basically, to make it become much smaller representation. So that's what we'll not call it self-simplifying machine. You know, so from a big network, you can simplify it dramatically using traditional techniques like regression pruning. But the second point, wait for our paper that will coming up very soon. Is what is the effect of regularization to number of LLM to all of those things. So we probably will have that very soon in terms of that. You know, so that is really pruning, because you can do many ways. I can do early stopping. I can do dropout, and all of those have effect of reducing the number of LLM to control the beast. Yeah, and many other techniques.
Yeah. Okay. So I think it's close to 1 o'clock, Agus. I know you had to run. Thanks so much for making the time. I'm going to make a couple of closing remarks. I'm going to collect all the questions, and maybe offline we can discuss. There are 19 questions now, so we answered like 4, I guess. So maybe if we can, you know, summarize some answers, I'll be able to like share that. So a lot of questions on like, you know, where the slides will be and where the video recording will be. I'm just gonna, I'll just share something for people who are interested. So
slide is available. I send it to you, right, Sri? So slide is available, video is available.
Absolutely. So what I've done is I put everything on Q Academy. So it's readily available, and I'll share a link to this for all the people who are attended. They'll get a link to it. So all the slides which Agus shared are going to be available in here. And also we have put the Alicia package on the sandbox. So you should just be able to like click on it, and then there will be this option to run it. And then we have just basically embedded Google Notebooks, Google Colab Notebooks. If you want to run it on a large scale, do let us know. We'll be able to like facilitate to run it on AWS. But right now you have all the Google code. You can just basically run through it. And I've also provided the links to where to get the data, the packages directly from GitHub in order to work on it. So I think that will be helpful. And as Agus was mentioning, we are going to be running a couple of workshops in winter. And the one which I would recommend is the Ponte University Machine Learning Management for model risk management for machine learning models. So this is going to be the third cohort in winter, and we have had people from the Fed, from OCC, from PwC, from Genpact. A lot of different companies have taken this course. So if you're interested, and especially if you're new to some of the concepts in explainable machine learning, interpretable machine learning, responsible machine learning, so you will get an orientation on these concepts, and we'll integrate some of these components we are discussing now as a part of the course. That way you will be able to get a 360-degree perspective of how to do model risk management, especially for machine learning models. So with that, I again thank you so much, August. It's always fascinating. I know I kind of switch my seats. I'm no longer in the podium teaching my students. I'm kind of sitting back as a student and taking notes. I always enjoy discussions with you. And thanks for this entertaining and fascinating talk. I think we are on the cusp of changing the way the world looks in terms of how interpretable models should be looked at. And you have the context, and that's why I'm very, very interested in your views, because we are not, from your world's perspective, you're not just sitting in an academic chair and thinking about concepts. You have to look at it from a practical perspective and apply it in the real world. And that's where I want to reinforce the concept that whatever we are doing should be practically applicable, especially in today's day and age, and when it's data driven. And with all the noise out there, we got to sift through the noise and kind of focus on the ones which are actually useful, and also something which, from a financial services perspective, can be made pragmatic. So with that, I will conclude today's session. Next week, we're going to have one more discussion on basically simplification and unification of models. And Ian Covert from the University of Washington has co-authored a paper with Microsoft and a couple of other researchers. So for people who are attending, feel free to attend that lecture, and we will continue the discussion online. Thank you so much, Agus. And
thank you, everybody. Thank you, everybody. All right, bye now.
Bye.